Hello people, so now we need to solve some more problems. To save on words, now we are just going to say solve the system. Obviously this stands for solve the following linear system using elementary row operations and Gauss-Jordan method. Too long to write, just solve the system. So first step, as usual, we write augmented matrix of the system. Copy the coefficients from the first equation, the first row, slash on the other side, the right hand side member, and then second row, coefficients from the second equation, and third row, coefficients from the third equation. Okay, so now we need to start our Gauss-Jordan process using elementary row operations with the goal to produce zeros below leading entries. We are lucky we have 1 as our leading entry, so it will simplify our life. So first thing we need to do is try to put 0 here, and we need to replace row 2 by row 2 minus 2 times row 1, and then we do the job. So 2 minus 2, 0, minus 1, minus 2 times 2, so minus 1 minus 4 is minus 5, and then 4 minus 2 times minus 3, so 4 plus 6 is 10, and 2 minus 6 times 2, so 2 minus 12 is minus 10. We need to produce 0 also in the third row, first entry, so this will happen when you do row 3 minus row 1, we get these numbers. Now we are all happy, we have our leading entry with zeros below. We hit the second row, this is our leading entry. We need to produce zeros below. Well, what we realize is that, oh, this is something cute, we can divide by -5, the second row, and simplify our life. So that's what we do. We replace row 2 by -1/5 times row 2. And we get these coefficients. Now my leading entry is 1, it's cuter, so I can go and eliminate the entry below. So that's where we are. So we replace row 3 by row 3 plus 3 times row 2, and we get the following result. Notice I'm not using row 1, because if I use row 1 on row 3, I'll introduce a non-zero value here, and I struggled to get 0, so I'm not going to destroy my work. So be careful about that. Be smart about it. So now I have this echelon form, beautiful, and I realize, okay, I need to divide by -2 the third row. So let's do that. I get my 1 as leading entry, and then I have a fraction. Well, I don't like fractions, but I need to live with it. There's nothing else I can do, just live with it. Alright, so I have my 1 and the fraction, so I need to kill this guy and this guy. So replace row 2 by row 2 plus 2 times row 3, do the job. Need to work with fractions, well, work with fractions, no problem. And then kill the -3 in the first row, do the work, get the job done, and then I have a fraction again. Well, I don't like them, but that's where they are. So now I introduced zeros above my leading entry, that's great. And the last step is to produce 0 here. So I replace row 1 by row 1 minus 2 times row 2 to kill this guy. Obviously these two need to work also, and you get another fraction. What can you do? You have fractions. So now I have my reduced echelon form, which is also, in this case, identity 3 by 3. And I realize that the solution is simply x1, x2, x3, where, well, x1 is equal to 7/2, x2 is -1, and x3 is -3/2. Ta-da! So it happens that I have some fractions, and I couldn't do much about it, or I was too lazy to do anything about it, and I computed with them. There's no problem at all. Might be a little bit uncomfortable, but other than that, it's fine. I have another example, again, just solve a system. I have my augmented matrix form, and now what's special about this one is that in the corner here, top left, I don't have a leading entry, I have 0. 0 is never a leading entry. So below I have 2 and 1. So it's clear that I need to swap. I need to move the row 1, I need to move it lower. So what do? Do I swap row 1 and row 2, or row 1 and row 3? Well, both of those operations are elementary operations, they are legal, they are perfectly fine. The question is, which one is useful to me? So the one that is useful to me is swap row 1 and row 3, because I'll get 1 as my leading entry here. So that's what I do. Row 2 stays as it is, I swap row 1 and row 3. This is the result. So now I have my leading entry queued, 1, and I need to use it to kill the 2 beneath. So again, applying elementary row operations with Gauss-Jordan method. The idea of Gauss-Jordan method is to apply elementary row operations to get the reduced echelon form at the end. So I apply, simply replace row 2 by row 2 minus 2 times row 1, do the work. Well, I realize that this is divisible by 5, so it will simplify my life. So row 2 replaced by 1 over 5 times row 2. I get cute numbers here, so now my leading entry in row 2 is 1, so I can use it easily to get rid of the 2 below. So now working on row 3 to kill this guy. So row 3 replaced by row 3 minus 2 times row 1, compute. I have my leading entry here, so this is echelon 4 again. So my echelon form is there, that's great. What I need now, okay, my leading entries are also 1, that's an extra. Now I need to kill these 2 guys. Simply replace row 2 by row 2 minus row 3, do the work, and replace row 1 by row 1 plus 2 times row 3, do the work. And this is what I get, so I have my leading entry with zeros above. So my leading one is here. And the last step to get my reduced echelon form is to eliminate this guy here, because this is my leading entry, it needs to be the only non-zero value. So I need to simply add row 1 and row 2, replace row 1 by it, and this is my reduced echelon form, which is identity matrix 3 by 3 also. So again, this system has a unique solution. x1 is 0, x2 is 1, and x3 is 2. Ta-da! My solution is there. So step-by-step process. What was special here is that I had to swap 2 rows. I had no choice. So now, another problem. Again, I'll just say solve. This one will require some creativity eventually. So here's the system. So I have a homogeneous system this time. It's just nice. So I have 2x1, x2, 4x3 equals 0. So this is 9. So this system is homogeneous because every single equation in the system is homogeneous. So if I produce augmented matrix form, it's easy. Okay, so I have my leading entry 2. I don't like 2. Oh, I could divide by 2, but I will introduce a fraction here. That's okay, there's nothing wrong with fractions, it's just that I don't like them. But if you like the fractions, you go ahead, just divide the first row by 2, and you will get your leading entry 1, and you keep going from there. Notice you will introduce a fraction, you will have 1 over 2 here. So that's one option, and it's all perfectly legal. There's nothing wrong with that option. Another option, a little bit more creative, is to perform an elementary row operation, one of the 3 legal ones, in such a way that I will get eventually 1 here. So there are several ways you can do it. It's maybe going to take several steps, not only one step. So one of the options could be, well, I'll say I replace row 1 by row 1 minus row 2. Okay, I'm going to get negative 1, fine, but then I will just multiply by negative 1 the entire row, and then I'll be fine. So that's one option. Let's try that one. Another one would be to work with row, let's say, 2 and 3, produce 1 somehow, and then swap rows. Fine, whatever you like. As long as you use elementary row operations, it's your choice. So let's try one of them. So my decision was replace row 1 by row 1 minus row 2. Okay. Just happens to be my choice. It could be something else. Or as long as I'm working with elementary row operations, I'm within legal terms, it's not a problem. So row 1 minus row 2, so I get minus 1. 1 minus 1, 0. 4 minus 6, minus 2. And 0 minus 0, 0. And then the other rows stays the same. They don't change. Okay. So fine. But I have negative 1. I don't like negative 1. So what do? Well, I'm gonna multiply row 1. So I'll replace row 1 by minus 1 times row 1. That way I'm gonna get one is my leading entry, and everything else stays the same. So from now on, I just apply my normal operations. I have my 1 in the corner, and I'm going to kill 3 by replacing row 2 as row 2 minus 3 times row 1 and row 4 also. So that's one way of doing it. Okay, so let's go. Row 2 replaced by row 2 minus 3 times row 1. So this will be 0. This will be 1 still. 6 minus 6 is 0. Nice. Okay. Row 3. Row 3 minus 4 times row 1. Let's write 4 clean. Okay, so this will be 0 obviously. So 1 minus 4 times 0 is 1. 9 minus 4 times 2, so 9 minus 8 is 1, and 0 here. Okay, so that's good. Now I need to kill this guy. I replace row 3 by row 3. So I have my leading entries. I need to put 0 below the leading entry. So I have this minus this 0, this minus this 1. Oh, I'm almost done. I have my echelon form. Look, I have my zeros below the leading entries. Leading entries are 1, great. But here it's not the only one in the column. So I have 1, 0, 2. So my leading entry is not the only non-zero value in the column. So this is still echelon form. Okay. We are not yet at reduced. Now we are going to get there. Row 1 minus 2 times row 3. Why? Well, I need to introduce 0 at this position here. 0 down, you always get 0. What? What does this mean? I have my reduced tension form. So I'm done, I stop. Now I need to find the solution. Well, apparently solution is x1 equals 0, x2 equals 0. So my unique solution of the system is unknowns x1, x2, x3, 0, 0, 0. Ta-da! That's what's called trivial solution because just 0. Great. So the idea was, at the beginning I had my leading entry that was not 1. So that's a little bit annoying. So what do? I can employ a couple of these operations, elementary row operations, to somehow get 1 there. So my choice was subtract row 1 and row 2. I got -1 in the leading position. Then I just multiplied by -1 the entire row. Now I'm good. You notice that we cannot multiply a row by 0. If we do that, well, we kill the entire equation. If you multiply everything by 0, well, all this is gone. You have 0 equals 0, finished. So you killed your equation. So we cannot multiply by 0. We can multiply by any other number than 0. Alright, so that was one option. Somebody could be creative and say, okay, let me say row 3 minus row 2, I'll get 1 and then I'll swap. We can do that. That's perfectly legal, there's no problem at all. So it's your choice what you do. Okay, there's no magic bullet. You could divide by 2, you will have fraction, you will live with fraction. The thing is, at the end, you'll get the same answer. So that's what matters at the end. So let's have another one. This one is cute, short. So what do I have? 3x1 minus 2x2 equals 0. And 6x1 minus 4x2 equals 0. So obviously you see that this equation is actually 2 times this one. So that's good news. That's easy to see. That means that actually these two equations, well, one of them is useless. It has the same information as the other one. We cannot just delete it, by the way, huh? So I have 3. We need to live with it. The system has 2 equations. Well, that's what we do. Now, there's no point of me producing 1 here right now. I'm going to introduce fraction for nothing. I have a factor between these two, so I can exploit that. So all I do is row 2 replaced by row 2 minus 2 times row 1. Do that, miracle happens. So 6 minus 6, 0. And then you have 4 minus 4, so 4 plus 4, negative 4 plus 4. Ba-bam. So here we are. Oh, there's no problem here. I have row zeros and on the other side I have 0. All good. No problem. The system is consistent and there's no problems. By the way, a homogeneous system, in your book it says it's always consistent. What does it mean consistent? It means it always has at least one solution. Because if you put x1 0 and x2 0, well, the first equation is 0 equals 0. Yes, that's true. And this one also 0 is equal to 0. That's true. So solution 0, 0 solves the system. So our system has at least one solution, which is 0, 0. So for homogeneous systems, one of the solutions is always 0, 0. Alright, so let's find here what are all the solutions. So from here I have 3x1 minus 2x2 equals 0. Well, I'm not in, this is just echelon form. I could reduce echelon form if you wish. It's not going to change much, but let's do it. Row 1, so 1 over 3 times row 1, so we get negative 2 over 3, 0, 0. So now we simply write the solution. So we have x1 minus 2 over 3 x2 equals 0, which means that x1 is 2 over 3 x2. So this is the expression for x1. x2 is free variable. And because x2 is free variable, that's where our infinitely many solutions come from. So a general solution of our system is, so solution is about x1 and x2. So x1 is given by this expression, 2 over 3 x2, and x2 is still x2, nothing changed, and we say x2 is a free variable. So this system has infinitely many solutions. So the system has infinitely many solutions. One of them is 0, 0. So if you put x2 equals 0, you'll have solution 0, 0. If you put x2 equal 1, you'll have 2 over 3, 1 as a solution. So we have infinitely many actually. For each different value of x2, we get another couple that is a solution.